local position space. So that's these gray. I'm just going to suggest maybe within some volume you distribute some gray, these gray dots as coverage points where you would want the system to be able to achieve by combinatorically applying some gates. Okay, so we'll store these in a list called these G goal motions, and if you want to weight them, depending on ones that you like more than others, that's okay. You don't have to uniformly distribute them. You could just say, I only care about moving forward and backwards, so maybe you just pick one axis in the body frame and bias your points that way. But regardless, the way that coverage is computed is I take each coverage point, I find the closest achievable motion, I take those 2 points and pull them back to the Lie algebra and compute the distance between them as a norm of the displacement in the Lie algebra. And after summing all of those points, that gives me what we're calling the coverage metric. So this goal function hopefully incentivizes the system to learn a collection of gates that allow it to be super locally maneuverable with a small collection of input gates. Okay, so let's take a look at an example where we have this 3-link viscous swimmer, and the space of I'm distributing the coverage points within a rectangular volume in SE2, which is where X and Y are the translations of the swimmer and theta is the orientation. So at this point, all this swimmer knows is this one gate that it tried where it didn't move anywhere, and that it wants to find gates that fill the space of rigid body planar motions. So over the sequence of iterations, it learns how to move forward and backward. Over the next sequence of iterations, it learns how to excite a new gate that starts turning it in one direction. And over the last sequence of iterations, it starts to fill this volume more fully, and it finds 3 gates that you can see right here. And it's not necessarily important what gates it chooses, it's just important that it was able to find a collection of gates where by combining them in different ways, it's able to explore its local position space. We kept adding joints to the swimmer to see if this would change convergence rates. I'll wrap it up. Each one ended up finding the same kind of convergence value, but the convergence time ended up being the same, about 1,800 cycles on the robot. So at the point of 1,800 cycles, you're starting to see these fairly aggressive maneuvers that search the position space. Finally, for future work, I'd like to implement this on hardware. That's very current work, and maybe there could be an investigation done as to whether mechanical redundancy is an asset or a liability, since these complex systems are learning quite quickly. Maybe even in the event of a joint failure, the system can relearn a coverage quite quickly. So thank you for your time, and I'm happy to take any questions.
Okay, Delisle is been shifted to Thursday, so Romeo, if you are here. Yep. Excellent. You can get your mic on. Questions for the speaker? Aaron?
Looking at those plots, it reminds me of RRTs. If you look at kinodynamic RRTs and compare that with kind of exploration.
Yeah. So, So in the case of applying RRTs here, we're being really careful with the regions of the state space that we're exploring, because the idea is to restrict the amount of experimental data that we're collecting. So if we were going to use an RRT method, I would need to actually experiment every time I branch the tree out to look for something new to do. The idea here is to take a bunch of cycles in the same region and build a lot of dynamical information in that local area. That's definitely something interesting that I think could be useful. For example, transitioning between gates, that might be a useful approach. Thank you.
More questions? Andy?
It seems like a different maybe optimization, which feels more efficient to me, would be to try to find the convex hull of a set of poses you could reach in one move. Mm-hmm. And then once you've found that, presumably you can do different amplitudes of each move, and it's not a theorem, but presumably you can interpolate between moves. So you have some shape, which is a convex hull of where you can get in one move, basically.
Yep.
And then you can pick different amplitudes in different directions, and if you want to go far, you always just pick points on the boundary of that convex hull.
Yeah.
Is that equivalent? Well, I just said it's an approximation, because I guess you can't really interpolate between points, but you probably can pretty close to do that.
Yes, so I think that this suggestion is
You want
a
to just translate that, so just say what I said.
sure. So you're suggesting defining a local space to explore that's somewhat constrained, that I can sample new maneuvers in, just pick the ones that work and just go from there. Might take less time.
No, I'm saying it's just a local optimization problem of just finding how far you can go in each direction in pose space in one move. And then
Okay.
composing all your later things on different amplitudes and interpolations of those points.
Yeah, I think that this could work, and maybe I'm not. I think maybe I'm not fully internalizing what you're suggesting, but the idea of like optimizing directly on the coverage metric is that along the way we're exciting modes that move in very different directions. So if I'm working on like SE3, which is a much more complex position manifold, maybe I'm able to move in a much versatile way that doesn't necessarily require extremality. Moving as far as I can in the pose space, which I think is what you were suggesting. But okay, maybe a
Yes.
discussion for later.
Do you have, if we could switch the laptops over, that'd be great. Is there one more?